Today we continue doing more examples and ideas about Newton's second law, Newton's third law, Newton's first law, using all those and especially the functional form of Newton's second law to analyze motion or equilibrium states where there is no motion. And we talked about some very important constructs today and some, therefore, very important tools to use to analyze certain situations. If we look at just a box resting on the ground, there are two forces acting on this box. There is the weight force, the force of gravity that's pulling it down, and there is the reactive force from the ground pushing it up that we call the normal force. So if we want to analyze the forces in the y direction, which is just those two things, we call the normal force small n, then we say that the sum of the forces is equal to the n vector plus the force of gravity, which equals, according to Newton's second law, it tells us the sum of the forces equals ma. In this situation, it's not moving, it's at rest, so the ma is equal to 0. And this would be, specifically speaking, the a and the y direction, since we're looking at the forces in the y direction. So then we have the n vector plus the fg vector is equal to 0, since we said the acceleration in the y direction is 0, since it's not moving. And if we plug in the directions for the n and the fg, we know that the n is pointed up, so it's plus the magnitude of n. The fg is pointed down, so it's minus the magnitude of n equals 0, or that the normal force is equal to the weight force of our object, which, as we talked about before, is equal to its mass times the gravitational acceleration of positive 9.80 meters per second squared. So if you knew this was 1 kilogram, this box here was 1 kilogram, that's 1 kilogram times 9.80 meters per second squared to give you 9.80 newtons of the force for the normal vector there. So that's a simple example of how to use the sum of the forces equals ma. Now, the normal force is only there because it is in contact with the ground. We have the ground pushing up on it. If this were water, that normal force would not be there. You'd have some other force from water, from friction from the water molecules. And the floor only exerts as much force as needed to balance things out. If the floor were exerting more force than the force of gravity, then these two things would not be balanced and the box would move up. So the two forces together determine the behavior of that box, that behavior being the ma. Okay? And n is not always equal to fg. It is in these cases where it's flat and not moving in the y direction, but we don't always have those situations. If instead you have a box sitting on an inclined plane, then things are different. Okay, we have some inclined slope here with, we'll call an angle theta, and we're going to have our box on here now. Gravity still always points down. Well, the gravitational force, pardon me, still always points down. So Fg is here. Okay. The normal force, the definition of the normal force is called normal because that means the perpendicular to a surface. Not normal meaning usual. Normal meaning perpendicular to a surface. So the normal force is perpendicular to the flat surface. So the normal force is definitely not going to be equal to the gravitational force in this situation. And if this plane is frictionless, this block is moving down. We haven't talked about friction yet, we will be doing that next class. So right now we have to assume there's no friction. So this block is going to move down with some acceleration, okay, unless it's being held by something else up here. Okay? Let's say, like we did an example problem in class where we had a tree, we'll call it a person here. A person is holding onto the box with a rope. So then we have this rope, we're going to call it the force that the box experiences from the rope, the tension of the rope. And we'll say that that is enough to make the box not move. Okay, so you're imagining you're at the top of that hill holding onto a box, not letting it move. So the forces that this box is experiencing are the normal force pointing away from the surface, perpendicular to the surface, the gravity force pointing straight down, and the tension force directed up the incline. Now, what we want to do to analyze this is to take our regular x and y coordinate system and tilt it to make an x prime and a y prime coordinate system which matches up with this incline. It makes things so much easier to do that. So we are always going to be doing that whenever we deal with inclined plane problems. We're always going to be looking at the coordinate system that lies with one axis along the incline and the other one perpendicular to it, because it makes the analysis so much better. And as long as you always have these two things being perpendicular, you're good. As long as you're consistent for the whole problem using it that way, it's completely legit to do that. Okay. So that means that our new axis for the y is this y prime here, and the new axis for the x is that x prime there. And that means that now we need to look at the sum of the forces in the y prime direction and the sum of the forces in the x prime direction. Fg lies along neither. And so we're going to have to look at the components of Fg lying on those axes. So we're going to make another triangle to figure out what an angle here or an angle there is, because we need to have it with respect to those axes. If we drop a line down, okay, and look at this triangle compared to that triangle, and actually if I move this down here explicitly so that we see that, or move this arrow over here, then we know that this angle right here is equal to this angle. How do we know that? This angle is 90 degrees. This angle is theta. The angle in the angles of a triangle add up to 180, so this has to be 90 minus theta, because this is already 90. So if this is 15, then that means that this angle right here is 75. And this angle is a 90-degree angle, so this has to be the 15. So what that really means is that this angle right here is equal to the same angle of this. And that's what we're going to pick to use so that we can be consistent. So the angle of the hill is that angle right there. So that means we're going to look at this component along the x prime, and we're going to look at this component along the y prime for the force of gravity. Okay. Let me draw the free body diagram over here. So the normal force up, the tension force back this way, and we have the force of gravity down here. So the sum of the forces in the y prime direction would then be equal to the normal force pointed up in the positive y prime, and we have the y prime component of the gravity, and that's equal to ma in the y prime direction, and it's not moving on the y prime axis, so that's 0. Okay? So plugging in the directions now, n is pointed up, like I said, so that's positive. This is minus, so it's going to be negative the y component of the gravitational force equals 0. So what is the y prime component of the gravitational force? What does the trig tell us? Well, we're looking at this side right here. Oh, that's the x prime. We're looking at this side right here for the y prime axis. So this leg of the triangle, if we're looking at this angle and using this as our hypotenuse, because that's what it is, that would be the FG as the hypotenuse, that means that we have the cosine of the angle to worry about, unlike our usual thing with y's, which is sines. So that means that we have n minus FG cosine theta is equal to 0. Okay, because we want this part of the component along the y prime. Or, plugging in, if we have the mass of that block, we have minus mg cosine theta there. Okay, so that's looking at the y direction. If we're looking at the x direction, then we have the tension, that's here in the x direction, and we also have the x prime component of the gravity, the part that's going down the slope. So we have some of the force in the x prime direction is equal to the tension plus Fg x prime, which would then be equal to ma x prime. But because the person's holding it in place, that's going to be 0. Okay? So the tension here plus the other vector for gravity is going to give you 0. Plug in the directions, and we have t going negative along x prime, and we have the gravitational on x prime is going to be positive, so that would be positive Fg, and the x prime part of this is this one right here. So that's the sine of the angle. So negative t plus mg sine theta is equal to 0. So that's how you would go about analyzing this and breaking this up, by changing your coordinate system, rotating it slightly, to make it lie on the plane. And so the normal force is not mg like it is if you're flat. If the plane is not, if it's not an inclined plane but it's instead flat, it's actually equal to mg modified by a number. It's equal to mg times the cosine of theta. And the tension there would be the mg sine theta. If the tension weren't there, if this person, if the rope broke, for example, and this tension were no longer there, then the block would move down the incline, because there's nothing that's stopping it from moving down. But you do have the gravitational force that is pulling it down. This t would be 0. This would not be 0 anymore because it's moving. You'd have ma, and so you'd have mg sine theta is equal to ma x prime. And then you'd be able to figure out that the acceleration is equal to g times the sine of theta when you cancel out the m's. But that's how you would approach that sort of thing.